Okay, so I hope you can see this slide. If you can't see it, then let me know. So last time we were discussing. Okay, so if you have a three-stage pipeline, there are three main functions: fetch, decode, and execute. So fetch stage is very simple. All it does is whatever the value which is given in
Sir, the screen is not visible.
screen is not visible.
No, sir.
Oh, that's interesting. Just 1 second. Okay, is it visible now?
No, sir.
No, sir.
It is a black screen.
Okay, so let me share it again. Any better?
Yes, sir, it is visible now.
Okay.
Yes, sir, it's visible.
Okay, thank you. So let's try with this. So this is your fetch stage. What fetch does is it goes to the special counter which says program counter. Now program counter has some memory address value. So when you first bring in the program, your program counter will be set to the first line of code. And that would be done by your Kyle compiler, or if you have operating system, then it will be done by that. So you will be, or your hardware will read this address, go to the memory location, fetch that first instruction from instruction memory, and then send it and bring it back, and then it will go to decode stage. So each stage is something like this. This is your clock. So first stage, at this particular cycle, the fetch stage will bring in the instruction. It has to finish work by this. At this instant in the second cycle, it will be sent off to the decode stage. After in decode stage, it will read operand if necessary. So for example, for add kind of instruction, it would read two source operands. It will also decode what kind of instruction it is, because in fetch stage it is all ones and zeros. Fetch stage doesn't know what instruction it is bringing. Only decode stage would figure out, and it would have hardware to figure out. It knows the location of each and everything. So it knows that from MSB, I mean, just for example, from 26 to 31, you have got your opcode. So 100111, just for example, say means add. So then it will send a message to the execute stage through the ALU, which is lying in the execute stage. Okay, I'm going to send you two source operands, R1 and R2, and you're supposed to do the add operation. So then it will, in the execute stage, it will do add operation, and then in the same execute stage, it will put the result back into register file. Now execute stage also takes care of load and store. Now, for 5-stage pipeline, as we are going to see in a very short time, that memory access stage is a separate stage. It is not part of execute. So, but here, since there are only 3 stages, execute also executes instructions like load and store. So basically within this execute cycle, for load and store, it may do address calculation for load and store, and then it will go to particular memory location and then put the result back into a register wherever it is required, or take a value from register and put it into memory location. So this is like a 3-stage pipeline. Now let's talk about the basics of ARM instruction architecture. ARM is a 32-bit architecture, which is partially true, or it is true for the type of processor which we are going to study. Now, processors have become quite good. So all your high-fly processor which are used in mobile, or which are used in just one second. Which are used in, say, high-end mobile phones, they are 64-bit. But otherwise, the processor which we are going to study, and for a very long time, ARM was exclusively 32-bit. ARM doesn't have 16-bit processor. I mean, it has always been 32-bit, and that was one of its strong points, because it was unheard of to have a 32-bit embedded processor in late 1990s or early 2000. Now, in relation to ARM architecture, byte means 8 bits, I mean, which is universally true, whether it is ARM or anything else. Half word means 16 bits. Now, half word means, depending on this, since it's a 32-bit architecture, half word means 16 bits. But if this were a 64-bit architecture, then half word would mean 32-bit. So anyway, for our purpose, half word would always mean 2 bytes or 16 bits. And word means 32 bits or 4 bytes to put together. Now, at this point, I would like to tell you that memory is always byte addressable. So what this means is that each byte has got its own memory address. So, I mean, in some cases, like, for if you are using some audio applications, does the 16-bit? Okay. Can you repeat that question? Can you speak up? It's difficult for me to read.
Good morning, sir. Actually,
Can you speak up, please?
Yes, sir. Good morning. Actually, I was asking, I didn't understand this 32-bit and 16-bit. I mean, what does it mean? What is the context? Does it show the processing capability of the processor, or?
No. It has nothing to do like that. These are some of the definitions. Now, half word means 16 bits. So as I told you, the thumb instruction set is 16-bit. So you can say the thumb instruction requires, basically, if you want to bring in a thumb instruction, you have to fetch a half word from the memory, right? So half word is just shows a quantity. If I say half word, that means 16 bits. Now you may have some memory which is 16 bits, or because as I told you, the 16-bit memories are cheaper than 32-bit memory. So sometimes, even if you are using 32-bit data, but you are working for some very cheap product which cannot afford the price of having 32-bit memory. So you will have to tell the program that you have to fetch 2 half words. So because it's only a 16-bit, so first half word would come, and then second half word will come, and then it will be joined together to make one word. right? So a half word basically means 16 bits. It can be used in any context that you like, but basically half word shows the size of the data or instruction that you're bringing in. I hope that answers your question.
Yes, sir, I got it. Thank you, sir.
Okay, now ARM has got two types of instruction sets, 32-bit ARM instruction set and 16-bit thumb instruction set, which I already told you what that means. Now, there is no one-to-one correspondence, that not for every ARM instruction, there is a corresponding thumb instruction. So there are certain ARM instruction which does not have a thumb instruction equivalent. Now, it is always, people initially when it started, I mean, this is what I'm talking about 1990s stuff, that, thumb instruction was used very extensively by low value electronic products that, for example, you want to make a toy or a toaster or something. You just want to put a 16-bit memory. Now it makes sense that if you are using only 16-bit memory, if your instruction is 16-bit, then, in just one go, you can bring the whole instruction and then, use it. If you're using 32-bit instruction, then, you have to make two trips to the memory, and that takes time. So at that time, 16-bit thumb instruction set meant a big deal. We are not going to ask you to program anything in thumb instruction set. But you need to know that there is something like thumb instruction set. Even within a program, you can write a part of the program in ARM instruction set. Then you can write rest of the program in thumb instruction set. But you need to let the compiler know. And then there is a particular instruction called BX. BX, you will read about it in the book, which says, okay, now you are switching from ARM to thumb and thumb to ARM. Again, if you use BX, then means you are jumping from thumb to ARM. And again, if you write BX, that means now you are jumping from ARM to thumb. Okay, now as I said, when we are talking about 32-bit data or memory, when I say bring in one word from memory, that means I want 4 bytes to come in together, byte 0, byte 1, byte 2, byte 3. So I will say that, instruction 1 okay, so that means instruction 1 lies at memory address 0. So when I say bring in a word from memory location 0, it means it will bring in 4 bytes together. Okay, so this is 0th location. This is location number 1, location number 2, location number 3, memory location. I'm talking in decimal. But it understands that when you say bring in a word from memory location 0, it knows it has to bring in 4 bytes, not just 1 byte. That doesn't mean you just have to bring in byte 0. It knows it has to bring in byte 0, byte 1, byte 2, byte 3. Similarly, when it says instruction number 2, so that means you have to go to memory location number 4. And when you say bring in a word from memory location 4, it understands it has to bring not only this byte 4, but byte 4, byte 5, byte 6, byte 7, so on and so forth. Right? So this you must understand. So then, when you want to give a word address, the first word would be at memory location 0, the second word would be at memory location 4, third word would be at memory location 8, so on and so forth. If I'm talking about thumb instruction address, the first instruction would be at byte at 0, the second one would be at 2, third one would be at 4, and this would be 6, and so on. Now, we also said that, that every cycle, that's the whole advantage of pipeline, and we are going to talk about it in the next installment of this course. But for this particular thing, the advantage of pipeline is that at any given cycle, multiple instruction would be in various stages. So for example, you pushed in instruction number 1 2 cycles ago. So now, instruction number 1 is almost ready to get out. It is in execute stage. Whereas instruction number 2, which was pushed in the next cycle, is being decoded, and then, it is being register selection is done. And at the same time, instruction number 3 is being fetched. So at any time in 3-stage pipeline, 3 instructions would be lying in various stages of completion. Now here you would see that there is thumb to ARM decompress. So there is an understanding that how to decompress thumb instruction and make it an ARM instruction. It does not take any additional time because it is all calculated for. So this is going to be done in one cycle. So if you push an ARM instruction, then this stage does not come into picture, and it's just ignores it. It just goes for decode and register select. Once again, not all thumb instructions can be decompressed into ARM. So in other words, there is no one-to-one correspondence between thumb and ARM. So there are certain instructions which cannot be nicely compressed into thumb instruction so that later on in this stage it can be decompressed and give the same meaning, because you might lose some data. So this is just in case if you have got written an instruction in thumb, it will be decompressed into ARM. So basically what it means is it will be converted from 16-bit to 32-bit. Now here you can see execute, it does a lot of things. It is doing register read, it is doing shift, it is doing some ALU operation, and then it is going to write into register. In 5-stage pipeline, things would be easier. That a lot of things would be, this execute stage could be broken down into 3 separate stages, and we will see just in few slides. But this is important. This is so you, 2 things you need to remember from this slide set. What it means is that memory, each memory is byte addressable. So this would have a unique address, this one would have unique address, this one would have unique address, and this one would have unique address. But when you talk about Word, or when you are writing a program and you are using 32-bit, when you say bring in a word from memory address 0, it means it will not only bring this, but it will also bring this, this, and this. So it's a package deal. So that's why your first instruction would be at address 0, second one would be at address 4, third one would be at address 8, so on and so forth. Okay, if you have any question, please let me know. So that's why, yes.
Sir, you said that not every ARM instruction can be compressed to thumb instruction. But sir, other ways possible, like every thumb instruction can be ARM instruction.
Okay, so what I'm trying to say is that, just let me. So let me just say that you have, say, 20 ARM instruction. Just suppose. Now, it may happen that I have only 15 thumb instruction and not so. That means for each ARM instruction, there is no equivalent thumb instruction. There are certain instructions which cannot be compressed. Say, for example, which is giving you some immediate address. So where you have to actually write address value. Now that address value cannot be compressed, right? So then, otherwise, it would create a problem. It will not be properly decompressed. So there are certain instructions which don't have equivalent thumb instruction. There is just ARM instruction for it. So in version 4T, there are 56 ARM instruction, and I'm not sure how many thumb instructions are there, but definitely less than 56. Okay, does that answer your question?
Sir, I am asking that do we have ARM instruction for every thumb instruction or not?
Yes, naturally. So basically, this naturally ARM instruction is like, can do everything what an instruction set can do. They have tried to make equivalent 16-bit instruction set called thumb, but they are constrained by the size, right? It's only 16-bit. So this is like, your spec sheet says 56 ARM instruction. This is what you expect your ARM architecture to do. Now, you say, okay, can I compress this in 16-bit? Well, some instructions are okay to be compressed, some instructions are not. So that means, you may get 45 or some number which can be compressed. So, you have lesser number of thumb instruction. But ARM instruction basically has all instructions which can do work.
Okay, sir, got it.
Now,
Thank you.
I mean, let me tell you that in the modern architecture, that means version 7, 8, 9, which is the most current, the distinction between ARM and thumb is gone. They just call it thumb 2 instruction set. So which means some instructions are 32-bit, some instructions are 16-bit, and whatever is better, they would do it. So it is known as thumb 2. This is just for your additional information or state of the art. There is thumb 2 instruction set. So it has got ARM plus thumb. So actually what I'm trying to say is it has got 32-bit instructions and 16-bit instruction all together. So some instructions are 32-bit, some instructions are 16-bit. And in fact, they encourage you to write a program in C language, even if you're working with embedded system and not assembly language. This is for most of the programmers and for current architecture. Except that you're working on a firmware, or if you're working on an audio application where you have to touch a particular bit and know the value of it, or you want to flip it for some reason. C can do the deal, and there are very good now compilers available which convert C into assembly language code. But this is all for Cortex-M. We are going to stick with assembly language for ARM version 4T, which is ARM 7 processor. And reason for that is this actually teaches you very well the concepts in computer architecture, because it tells you what happens at each and every stage. Here, you will only remain a programmer, and you will never be become architecturally aware. Here also in modern processors also there are certain times where assembly language program is absolutely essential. Just like I told you that if you want to know a value of a particular bit, or if you want to flip a bit for audio applications, for designing a game or something, then you have to have good assembly language programming skills, even for the processors which are using thumb 2 instruction set. Okay.
Sir,
Yes.
sir, in the 58 slide, each instruction is consisting of 4 bytes, right? Because we
Yes.
considered a 32-bit system.
Right.
Okay, so if it was a 64-bit, then it will be double.
Yes. So first instruction would be at 0th, second one will be at 8th.
And yes, sir. And this number of instructions may vary from the versions of the ARM machine.
I'm sorry?
And the total number of instruction can vary from the version to version.
Yes, sure. See,
Okay.
you can use ARM version 40 instruction into the latest processor, which is complying to ARM version 9. ARM architecture version 9, for the simple reason that everything has to be backward compatible. Just like in your Windows, if you've written a program in older version of Word, it has to work in the newer version. Otherwise, there would be riots in the street that people would get up and start shouting that why my program is not working.
Okay.
Someone else also asked a question regarding pipeline. Can that person speak up?
Yes, sir. Good morning, sir.
Good morning.
Sir, my question was that, sir, we say the three-stage pipeline. Sir, what do we mean by a pipeline in that context?
Okay, I didn't want to get too much into it because we are going to talk about pipelining, for the rest of the. So I think from after 1 or 2 lectures, we are going to talk about pipelining all the time. But anyway, if you are interested, let me just give you a short view. Like, say, for example, you say that you have got 3-stage pipeline. So physically, you would like to draw 3 blocks, right? And this could be, say, in the first stage, I want to do addition. In second stage, I want to do multiplication. Let's forget about processor. It is doing it's a very simple thing. This is first stage, it is doing addition. Here it is doing multiplication, and here it is doing division. And suppose you are sending a data, and data is somehow coming here, that first that data has to be added. Then the answer goes out here. Then it has to be multiplied with some other data which I'm sending in. The output goes to the third stage. And then, that particular thing is again going to be divided by the new feed which I'm sending in. The answer has to come out here. Now, I can do everything in just one big block that, I'm sending data here and then, taking inputs like this. And then, first, this 2 things, would be added, and then, the answer will be coming out here, and then it will be multiplied, and then, this thing would come in, then it will be divided, and the answer will come out here. So everything is doing in a black box. Here I'm just shoving in inputs. So like first 2 operands and third operand and fourth operand. And I get an output, which is I have received from this operations altogether. Now, this thing was done, the idea for pipelining came from assembly line, which was used by Ford Motor Company. So I'm giving you this example, which I would have given you after 2 days. So in Ford Motor Company, Henry Ford was a great innovator. He saw that, the people are making cars in a different way. At that time, the car of Model T was the first car which was invented by Henry Ford. So like, a big group of people would stand around a kind of a workshop. And let's say there are 5 things which needs to be done. So the first thing is you fit the chassis. That means you make the skeleton of the car. The second is engine. So, once the chassis is ready, someone would fit engine into it. Then the third unit would come. They would put all the electrical wirings and everything. Then fourth team would come. They would put seat, steering wheel, all the amenities that you get. And the fifth team would come and then paint it. Okay, I may have flipped some of the stages, but let's assume there are 5 basic operations which are done or required to make a car. So in Henry Ford's time, car would just constructed in the middle. So just like this, like one which I have shown you here. So just like this is the central pit. And here the first team will come and would assemble the chassis. At that time, other 4 teams would be standing idle. So the engine team would say, oh, we can't put engine till that particular car is ready or chassis is ready. Same thing, about the upholstery guys and steering wheel guys and painting guys. They would say, okay, we can't do anything. We are just standing idle. Then once the chassis guy fits it, then it goes to engine fitting guy. Again, 4 teams are idle. So he saw that, at any time, only 20% of the people are working. So how do I make all 100% of the people working? So he had this brilliant idea. He said that instead of people coming to work, right, on the central pit, I'll make sure that work will come to people. So he made people stationary. So he designed 5 stages or stations. So car will slowly keep on moving. So first, when it is in the first stage, someone would fix up the chassis, then move to the second stage where people would start fitting engine. At that time, again, first stage would start building chassis. After fifth cycle or after fifth station, once it is painted, all stations are busy because at any time, one first team is building chassis, second team is putting in engine in the car which was brought in previously. Third one is like painting, which was brought 2 cycles earlier, so on and so forth. So that is the advantage of pipelining, that all stages are busy all the time. So your hardware is always busy. And then someone would say, okay, I don't want to go much deeper into that, but this is the story of pipelining.
Yes, sir, means it means the separation of the operations into several
Correct.
stages.
And the advantage is that everyone is busy all time. So all 3 units would constantly be busy. Whereas here it's a black box thing. Unless all 3 operations are not done, you can't send in second data. Whereas here you keep on sending data every cycle. If you break this up into 6 cycles, work would be done even faster. We'll talk about it after 2 days. But this is
Okay, sir. Thank you, sir.
okay. Okay, so now, as I told you earlier, that instruction number 3 would be here, instruction number 2 would be here, and sorry, instruction number 1 would be here, 2 would be here, and 3 would be here. So what it means is that instruction which has already reached here is an old instruction. That means this was fetched 2 cycles ago. This instruction was fetched 1 cycle ago. And this instruction, and this is PC address. So this instruction was fetched just now. If it is thumb instruction, then naturally it's 2 bytes. So it is PC minus 4, PC minus 2, and PC. You need to remember this when we start talking about interrupts and which instruction has caused interrupt in which stage. Based on that, you will know how much to back up. This thing would become clearer in a couple of slides. But this is how you would say that if I got 3-stage pipeline, if I take a look at it, the instructions which has reached the 3rd stage was brought in 2 cycles earlier. So it is almost, it was already fetched, it was already decoded, and now it is in some stage of getting executed. So the address of that is PC minus 8. So this PC means the current program counter value. And this was like 8 bytes before that. So that means this is, if you see a program counter and if you see memory locations, instruction memory location, if this location is given by the value given in PC, then this value would be PC minus 4, and this value would be PC minus 8. Right? We are talking in terms of bytes. Sometimes, you will see that people talk about PC gets PC plus 1 to bring in the next instruction. So they're not talking about 1 byte, they're talking about 1 word. So instead of writing 4, that bring in the fetch the next instruction, they just don't say PC plus 4. They would say, okay, get me PC plus 1. So we may use this interchangeably, and you will basically understand when I'm talking about it. So next instruction to be fetched here after PC would be PC plus 4, PC plus 8, so on and so forth. This is for detail. I'm not going too much into it. You will understand this. Before we jump into my interrupt model, you need to know, you must be wondering that, you are given 2 instruction sets. You are saying it is saving memory. So which one is better? Is ARM better or thumb better? And, here is your exact answer. This is your performance scale, right? So, here you will get performance on, say, y-axis. This is, 1 second. This is x-axis or y-axis? The horizontal is x-axis, right?
Yes, sir.
Okay.
Yes.
Okay. So y-axis is your performance and x-axis is your memory width. Now, the one which is given in orange, it says the performance of a program which is written using ARM instruction set. And the same program, so suppose you have to write a merge sort program and you have written that program using ARM instruction set. And you have written that same program using thumb instruction set. Now, you are executing that program, you have stored that program in 32-bit memory. When I say 32-bit memory means both instruction and data memory are 32-bit. Now I'm running through, and processor is definitely 32-bit because ARM doesn't have a 16-bit processor. So for ARM instruction and thumb instruction, your test setup is 32-bit processor and 32-bit memory. Now you see the performance of a program which is written using ARM instruction set is better than the performance of a program using thumb instruction set. And the reason for this is obvious. Obvious in the sense that, as I told you, there is no equivalence between ARM and thumb instruction. That, there are specific ARM instruction for which there is no thumb instruction. So that, to do the task of that thumb instruction, you might have to use 2 or 3 thumb instructions repeatedly to do that task. It is not that you can't do that task, but you may require maybe 2 or 3 or 4 thumb instructions to do that task. And that takes time. You have to go and fetch it, go and fetch another one. So the size of your program in 16-bit, if it is written in 16-bit thumb instruction, it would be the length of the program would be slightly more. So if you're using 32-bit memory, it makes sense that you write your program using 32-bit ARM instruction set. Now comes the problem that you are designing a cheap system. You are using only 16-bit memory. And don't say that now 16-bit memory does not exist. We have 32-bit and 64-bit memory. So these cases are all legacy cases. No, people are still using 16-bit memory. And why electronics is so cheap? Because they worry about saving each and every penny in each and every stage. So if something can be done with 16-bit memory, they will not use 32-bit memory. So here, as you can understand, the execution of a program which is written using ARM instruction set is slower than the execution of program using thumb instruction set. And why is that? The reason is that each ARM instruction is 32-bit long. But the memory I'm using it both for storing instruction and data is just 16-bit. So that means to fetch one ARM instruction, I have to go to memory twice. First go and fetch the half instruction, and then go to the memory and fetch the second half of the instruction. Whereas for thumb instruction set, each instruction is only 16-bit. So I have to go to memory only once. That's it. So that's why the performance of thumb instruction set is increasing. Now, you might be observant and you may say, then why should the performance of thumb instruction set be smaller here than the performance of program which is written using thumb instruction set over here in 32-bit memory? Shouldn't they be the same?
Because it can fetch 2 instructions at a time because 16 bits.
No. Because at a time only one instruction can be executed. See, even if your data path is 32-bit, only 16-bit would be sent with all zeros in front. So that, because if you send 2 instructions at a time, you don't have an inline processor, you don't have mechanism to separate them out. The reason it is different is that though your instructions are 16-bit compressed, your data is always going to be 32-bit, right? So here, for thumb instruction set, for instruction, you just have to make one trip to the instruction memory and get the instruction. So you save time as compared to ARM instruction, because ARM instruction will have to make two trips. First, go in and bring the second half of the instruction, and then go second time and bring in the first half of the instruction and join them together. But data is 32-bit. So both, whether the program is written in ARM instruction set or thumb instruction set, to get the data, they will have to make two trips. And that is the reason why the performance of thumb instruction is less than in 16-bit memory architecture is less than performance of thumb instruction set in 32-bit architecture. So now they say that, if you have a little bit of luxury of having 32-bit, and this is what people are doing now, that, put a small amount of 32-bit memory just to store your data. And if you do that, then, some of your data would be coming here and the performance would be faster because, now you have to make only one trip. So you have mainly a 16-bit memory and a little bit of 32-bit stack. And you can see there is a good amount of increase in the performance of your thumb instruction set as compared to ARM instruction set. So this you need to remember for the sort of analysis. Now you may say that ARM instruction or thumb instruction are not, that important. But, this is, you must remember, because you will always have constraints. No matter, now you may say that, my processor is blazingly fast, I got lots of memory, but, still it is not enough. It is never enough. For current AI applications, you require tons and tons of memory. Like, for example, absolute facial recognition in shortest amount of time. Let me give you one example. Ideally, any security agency would like to put cameras in airport or railway station. And, when people are moving around, they can pick out person of interest, person who have been like, whether in the list of terror or, list of, known offenders or absconders or whoever. They can immediately pick them out. But to do that, so much amount of calculation requires to be done that, what is it that you have now, even that feels like a small thing. So you will always have to worry about analysis part that, how can I make things faster, given that I have constraint of resources. So whatever constraint of resources you have in the smaller system, very similar thing you will see in higher system, because computing power and memory would never be enough for any given problem. Okay, now we are coming down to the first meat of our thing. Remember, I said that at any time you have 16 registers and 17. So 17 registers, I made an assertion that, at any time, you have right? This is the assertion I made that, from R0 to R12. So these 13 are general purpose registers. R13, R14 and R15 are special registers because, they're designated for storing a special kind of value. And this is known as current program status register. So this, and this. So total, you can see R0 to R15, that means 16, and plus this is 17. Don't consider this SPSR because SPSR is a stored register, somewhere else. Now we are talking about interrupt modes. And types of interrupt. So each type of interrupt, these are given as the types of interrupt, and they're all connected to a mode. Now, why are we talking about interrupts and what is an interrupt? So again, I'll refresh your memory. that all smaller processors, particularly, are totally interrupt driven. So I'll give you an example of your washing machine. The processor in the washing machine is always sleeping. That means saving power. Only when you press a button, it would send an interrupt signal to the CPU. And okay, yeah, the user want to send you some signal. Now that signal would be select the size of the load which you're putting, whether it's a small load, medium load, large load, or extra large load. The second button might say that, what kind of cycle you want. Third button may suggest when you want hot water or regular water, so on and so forth. So these are the various interrupt modes. And as I told you, the smaller types of embedded processors works totally on interrupt-based modes, that they wake up only on interrupt. Whereas your laptop, because in your washing machine, there is no user program, right? Who's going to type a program and execute it. It's all interrupt-based programs. All you do is just press a button. It would send an interrupt signal. Interrupt signal will call a predefined interrupt handler, means a small piece of software code which is written. It will come executed. Once it is done, it exits and processor goes back to sleep. In your laptop, okay, the things are slightly different. But still it has to work with interrupts. Interrupts might be coming from your keyboard, might be coming from a pen like this, it might be coming from your mouse, or you might be downloading something, or your program might be crashing inside. So everything would send an interrupt, mainly from external sources. So here, the smaller ones, there are interrupts that we are studying, and what happens because when you talk of interrupt, immediately second question is, okay, it's fine. You said there are interrupts coming from various buttons that you're pressing in your washing machine. But how they would be serviced, how it would know what to do in that case. So here's your answer. Suppose this is your user mode, right? Don't look into this. This is your user mode, and in user mode, this is your user mode. Can you see the register? I mean, this is my slideshow.
Yes, sir.
Okay. So this is your user mode, R0 to R15, and then this is CPSR. This is current program status register, which we are going to talk about in the next slide. These are the registers which are allocated, of which R0 to R12. That means these are general purpose register. You can put any variable in it. You can store any operands in here, or you can store any final answer in here. You can do whatever you feel like. These are special registers which we are just going to talk about. And this is current program status register. Now, you are in user mode, and you are executing some of your program. Now, these are the interrupts. FIQ means fast interrupt. Now, I need to get out of this slideshow mode. Otherwise, I cannot use my pen. Okay, so this is FIQ, stands for fast interrupt request or fast interrupt. IRQ stands for normal interrupt. So these two are external interrupts. That FIQ, that means fast interrupt, and this is normal interrupt. Other interrupts are internal, like if you have put in undefined instruction, or you have given a memory address which does not exist, so that will be taken as undefined kind of an interrupt. So what happens is this: Suppose you are executing your user program. And your user program can be anything. Your user program, you are doing this. And suddenly, you have come up to abort mode. Abort mode means either it is data abort or instruction abort. And what it means is your load or store instruction which has come written into your program is pointing to a memory location which does not exist. And this is a very practical thing. It happens a lot of times when you change from one company's say microcontroller to another company's microcontroller. As I told you, that programmer needs to know 4 things: interrupt architecture, number of registers, memory architecture, and instructions. So memory architecture changes. Different companies give your small slices of memory which is placed anywhere in that address range which is 0 to 4 GB. So it may put address starting from some middle point to some another middle point and something. If you have written your original program keeping that in mind, and if you buy some new microcontroller board from some other company, and companies do that, right? Okay, this company has increased the price of its microcontroller containing ARM7 processor a little too much. So let me change over to another one. And if you change over to another one, and if you're pointing to a memory location which does not exist, either for fetching an instruction or storing a data or getting a data, then it will be called as either instruction abort or data abort. So then your processor would throw something like this. Now what happens? You are executing your program. You have written a merge sort program. Suddenly it stops at that point. Hardware is putting a brake on the execution of merge sort because the instructions which you brought in, either your load or store instruction, is pointing to a wrong memory location. Then it would say, okay, you have to stop what you're doing because I have to bring in an interrupt handler. There is an abort, some kind of data abort or instruction abort interrupt has come in. So it has gone into data abort mode or instruction abort mode. And to service that, I need to have some instructions. And what is that? That is another program. But that program is written by the manufacturer, not you. But though that is also written in ARM instruction set. So it would say, okay, I have to bring in that program. So what it would do is, it would go to this, it will have to do certain things first. First of all, your user program has to relinquish the control of the processor. And remember, this thing happens in your laptop also. That anytime you click a mouse or click a key, and there's some program is being executed. This is happening every time, and you see how complex the processors are. As soon as an interrupt comes, all these registers have to be saved into a stack. So there is a stack which is given right here. The stack memory is bigger than this, but I don't want to overwrite on this. So they immediately say, okay, save R0 to R12, all the registers into this stack memory. Okay. Then your program counter value. That program counter value will change because it will be replaced. Your hardware will say, okay, I will pushing out your program counter value. Program counter value is the last instruction of the program that you have written. It will point at that. But this say that I will have to replace this with the interrupt handlers PC. So this will be overwritten. If you want to save it, it's up to you. So then it says, okay, I will save it into the LR. So this is the user mode. I mean, it has slipped over here, and I will show you what would happen. So this program counter would be saved into link register. Now you have put this into stack, and stack is fairly big. Where you are put in, you have to remember that stack address. So R13 is used as a reference to the stack pointer. Now stack pointer, depending the way this thing is designed, might be pointing to the top of the instruction or the bottom of the instruction. That is dependent on the designer. But anyway, the stack pointer will be stored into R13 and this one will be stored into R14. So let us look at again, this I should again, go back to the full screen mode because then, you can see the animation. Okay, so this is your user mode. Suddenly the interrupt has come in. So first thing you have done is you have saved your R15 register into R14. That means program counter value is stored into link register. And all these things, R0 to R12 have been stored into the stack. And the value of the stack pointer or the address is now stored over here. So this is like a reference that, when I want to bring it back over here, I will use this value and then, start restoring it back. So, okay, these two things are done. Now you'll see that most of these interrupt modes, each one of them has got its own R13 and R14 registers. It is absolutely essential that all of them have their own R13 and R14. So this values which are stored over here, this program counter value is stored into link register, which is R14, and the stack pointer where you have saved it is stored into R13. These two things should not be wiped out. If it wipes out, then, when you come back to user program, you don't know where to start from. So that's why minimum, each interrupt has got its own R13 and R14. It also has its CPSR. So this is what would happen. You are in user mode. And suddenly, let's say, first I don't want to get FIQ. Let me say, suddenly, this IRQ, this interrupt request has come. So what would happen is it would use R0 to R12 of this. These are common registers to be used by user mode or any of this interrupt mode. So it would say, okay, I'm going to override this, but thankfully your hardware was smart enough to save R0 to R12 beforehand. So when the interrupt handler comes, the values which were there before into R0 to R12 are going to be wiped out. And that is the reason why you should save the user content into this stack. Then it would say, I'm not going to use the R13 of the user program or R14 register of the user program. I'm going to keep it as is, but I've got my own R13 and R14. So I have my own stack pointer and my own link register. Of course, I'm going to override this program counter, and I'm so going to use up this CPSR. So when an interrupt comes, your program has to follow, or your laptop or your computer has to follow this particular course of action. As soon as the interrupt comes, thing to do number one, save R0 to R12 of the user mode register values into a stack pointer. And save the stack pointer value in this R13 register. So our case, this one. Save your program counter value into R14 as a link register. And save your CPSR value into the SPSR of whatever interrupt has come. It has got its own SPSR. So you say, okay, I'm swapping, I'm putting my user CPSR value into save program counter register of yours, or whichever mode is called. Put it in there, and then user mode say, okay, I'm out. Now let IRQ mode handler come in. IRQ mode handler is nothing but a software program, another software program which is pre-written by the manufacturer, or if you're working in a job in a semiconductor industry, then it will be written by you. And it has got a recipe how to get out of it. Now there are various ways of getting out of it. I mean, the first way would be that, if you have already pointed to a wrong area of your memory and there is nothing, then, what is your handler going to do? So your handler would nicely say, sorry, it will give you a message on your window that, sorry, you are referring to a memory location which does not exist. And then it would say exit. And then, your program will be terminated. So now you will say, what good is it? Well, if it were not there, then your processor would be hanging. You have written a particular instructions, a load instructions that get something from this particular memory location and load it into register. But that particular memory location does not exist. So your processor would be confused that now what do I do? There is nothing, there is no interrupt handler, so I can't do anything. So then your system would be permanently hung unless you hit the reset button, and that means everything is out. Sometimes it does happen that your interrupt handler gets confused, or there is some error or some unseen mix of error comes in, and your system hangs. But most of the time, if you have written your interrupt handler in a nice way, it says graceful exit from that particular user program, because if one user program fails, you can do something else. You don't want your computer screen to freeze. So this is what your interrupt handler does. Now, as you see, this normal interrupt mode has got 3 registers of its own, that is R13, R14, and SPSR. Most of the interrupt handlers has that except FIQ. FIQ is known as VIP interrupt, and it has to be executed faster. So what is good in FIQ? That in FIQ, when the FIQ interrupt comes, it says, I have got not only these R13, R14, and SPSR of my own, but I also have R8, R9, R10, R11, and R12 of my own also. So what it means for you that you don't have to save R0 to R12 when you come out of the user mode. We just have to save R0 to R7. Now you may say that, okay, so you have saved 5 registers less, but you must understand, saving each register takes 1 cycle. So if you want to save 13 registers, it would take 13 cycles. But FIQ is supposed to be a VIP interrupt. So you want to execute it very fast, faster than any other interrupt. So you say, okay, I will service this interrupt only in 7 cycles. Why? Because it has to save only R0 to R7. That means in 8 cycles. I have got those. I just have to save R0 to R7 and R8, R9, R10, R11, R12. I don't have to save in case I've got a fast interrupt. So in real terms, if I'm designing a home security system, I've got several interrupts which are coming to my processor. There might be one interrupt which is coming from temperature sensor, and based on the input from temperature sensor, my processor might be turning on the AC. Or there is a light sensor, that is another IRQ which is coming from light sensor, which says light is low. So my processor might be ordering the lights to be turned on. There might be humidity meter, third IRQ coming from humidity sensor. And if the humidity is higher, my processor might send a message to dehumidifier that, okay, reduce humidity, so on and so forth. But there is one very important interrupt, which might be a fire detector or a smoke detector. If an interrupt comes from there, I don't want it to wait. I want to service that thing as fast as possible, because as soon as that interrupt comes, my processor has to service it and turn on the fire alarm or sprinkler or whatever as soon as possible. So, or if you want to take it in a medical condition, if a patient is having a heart attack, that particular sensor, which is a heart monitor, I want to give it highest priority. So if I want to give it a FIQ, that means that this particular signal coming from this particular sensor, I want to give it a highest priority. And if I want to give it a highest priority means I have to give it a VIP status. That means it has to be executed in lesser amount of time. So to do all that, my fast interrupt has got more registers of its own, so that if I want to come out from the user mode, I have to spend less amount of time saving into stack. And I can execute this fast interrupt mode as quickly as possible. Is this point clear to everyone? Does anyone have any question? Okay, so let me go for animation, and I think you understood. So when fast interrupt, when there is another interrupt which comes, this is known as service interrupt, and service interrupt basically is a software-based interrupt and which you have put in on your own. Like if you want to put breakpoint. Breakpoint means you want to have want to see at each stage of the program what values are coming out, the intermediate values. So it was I gave you example. You were writing when you were writing C program in the beginning, or when you have very long and complicated C program, you want to put a lot of printf statements in the middle of it so that you can see what is the intermediate value. So you can do actually hand calculation and figure out that okay, this answer is correct or this answer is not correct. So that is like a service interrupt. This is undefined instruction interrupt. So if you have written an instruction which is undefined, you will get this. And I'll tell you about when that would occur. And then finally is abort, which is either your data abort or instruction abort. So this is how it would function. If it is undefined instruction, then in that particular mode, it has got only 3 registers of its own. So that is how this thing would be taken. And abort, this would be taken. But when it comes to FIQ, you will see that saving is to be done only for this. And user register can retain all these registers starting from R8, R9, R10, R11, R12, 13 and 14 instead of just 13 and 14. So saving is also less. I just have to save R0 to R7. So this is the interrupt model which is given. And the advantage of this interrupt model is that very important for an embedded processor because everything is working based on interrupt. Now, you may have understood FIQ well, you may have understood IRQ well, you may have also understood service, and you may have also understood abort. That data abort means either to load a data or store a data, you have not given proper memory address or memory does not exist wherever it is pointing. Then you get those aborts. That's fine. But what is undefined instruction? So this is the last thing which we are going to talk about in this lecture. Now, undefined instruction is not something that you have done a kind of a spelling mistake. Instead of LDR, you have written LDP. I mean, those things are caught right in your programming environment where you're writing this program. That would immediately catch that particular thing. So it would not even come to a processor level. Now, undefined instruction is, suppose you have got a processor which is compliant to ARM version 4 architecture. And you are trying to feed in a program which is written using ARM version 5 instructions. So now that processor which you have done may or may not understand all the ARM version 5 instructions, right? Because version 5 instruction set may have all the instructions which are based in ARM version 4T, but it has got something extra. So those extra instructions, if they come into a processor which is only ARM 4T compliant, it would say, I don't know what this instruction means. So it would immediately throw an exception known as undefined instruction. Right? So that is the purpose. But people are using it in a very smart way. They are using, say, normally if it is undefined instruction, the interrupt handler will catch it. And again, just like abort, it would also send a signal to your screen that your program has written an instruction which is not compatible with this processor. So your program is terminated. And it would gracefully close your program, user program, and then get out of it. So your system will not hang. But in this particular case, people can make very clever use of it. And the clever use is this. Suppose if your client comes to you and says that, your version 40, you are telling me that, for most of the time, your version 40 compliant processor is good enough. It is very, very cheap, right? Because it's an old processor. developed in 2000 and that is good enough for my requirement. But I need one instruction called matmul, that is matrix multiplication. I mean, I'm so much used to writing my programs in matmul because ARM version 6 has got matmul instruction. So can you do something that I may still use a processor which is only version 40 compliant, but somehow my matmul instruction does not go give me an undefined thing and stops the program execution. So they will be told that, I mean, if you are a very clever programmer, you will say, yes, I can manage that for you, but it will cost you money. So what you will do is, you will say, okay, you can start using matmul instruction in your program. Now, matmul instruction, when it comes to here, this, very naturally, your processor, which is only ARM version 40 compliant and doesn't know what matmul means, would throw an undefined instruction exception. But you are smart. You have written an interrupt handler which would break down this matmul instruction into a legitimate ARM version 40 ARM instructions. So it would say, okay, if this particular instruction comes, you are supposed to use this series of instruction to get the value and then return the value and then say, okay, now your exception is serviced, I'm getting out. And the value, I've already put it into that register. See, so that is a clever thing which people use for undefined instruction. I mean, you can't do it for lots of instruction. You can't say that you keep on using ARM version 40 instruction, but I will write interrupt handler for all the instructions which are defined for ARM version 5 and make them run on ARM version 4. Because then you're making your processor very slow. So you can do it for 1 or 2 instructions, and people are actually regularly doing this. That they may say, okay, I will break down your ARM version 5 instructions into some legitimate ARM version 40 instructions. It may take 4 or 5 instructions to just do the work of one ARM version 4 instruction. Yes, if someone wants to make a statement or question?
Sir,
Yes.
in this case, you told that we added an instruction called matmul, for example, in the undefined.
Right.
But sir, now if an instruction come which is really undefined out of this matmul also, then now how it will handle this case?
Okay, good. So the question is that you have written some other instruction like integrate or INT. Now that particular instruction is not defined because you are not going to write interrupt handler for each and every instruction. So of course your interrupt handler has to be smart enough, so it has to figure out that matmul, if matmul comes, only then I can solve it using this. Any other type of undefined instruction, you will get a nice message on your so it is like a case statement. You write case statements, right? If it is this, then do this, else just give a nice message that okay, your program is terminated because of undefined instruction.
So we can give multiple things like instructions that are undefined also.
Well, I mean, it is not always the best idea, but you can do it for 1 or 2 instructions if your client forces you to do it.
Okay, sir.
But it's not a perfect way to do things. This is known as jugaad, right? Okay, so let us stop at this point, and in next lecture, I mean, still for lab purpose, I'm still having problem because the TAs have not been assigned. Instead of TAs, the number increased, the number is decreasing because the first year TAs have their own labs, which is clashing. So we will not have lab this week also. We'll compensate it in the other weeks which are to come, to follow. But I have given you enough data where you can actually start using this particular thing, write the first program. In fact, there is not too much of a need for a TA because there's quite a few examples which are given. You can start using them. You can start using individual instruction. You can ask yourself, if I want to write a merge sort program, I know the algorithm. But if I want to write the merge sort program, how can I write it using this 56 instruction? In fact, on the net, n number of programs, you will find which is written using ARM version 4T. So you can start if you are in a hurry, and then if you really want to learn, you can start learning on your own. Otherwise, you can wait for TAs to do it. But I hope every one of you have downloaded Kyle compiler on your laptop. It won't be loaded on Mac, as I told you earlier. So you have to have a Windows laptop. And please study chapter 2 to 6 minimum, because and the chapters are not too big. So please read, and we'll meet again on Monday. Okay, does anyone have any question? Okay,
Sir?
so yes.
Sir, where will this stack will become? Means it's of registers or in other memory?
No, it can't be registered, it is other memory. But stack is a special memory. As I told you, the memory location is like, address starts from 0000 to 4 GB. Now your stack could be anywhere. So right, stack is also a memory. So, just like your instruction memory, data memory, you put your stack somewhere, boot memory, and, you also defined a stack somewhere. So stack is also a type of memory. I mean, basically it is a memory, but you call it a stack.
Okay, sir.
હજી ચાલુ છે મારે.
Okay, so thank you very much. And we stop here.